Students, today we are going to start the lecture number 12 of the course on material informatics. I hope last 11 lectures had made you believe that machine learning must be an integral part of material informatics. Why? Because we are handling data and going to make predictions based on the analysis of data. So, therefore, we need to use some models, right. So, most of these models which we are discussing or we have been discussing for the last so many lectures are basically based on statistics, and some of them are based on probability. So, I have discussed about the Bayesian probabilistic algorithm, which is based on the Bayesian theory of probability. So, therefore, statistics and the probability form the very important base, or rather fundamental base of machine learning and material data informatics. Today, we are going to learn a new technique or algorithm called decision tree, or what is popularly known as a DT in the literature. So, please focus on your attention so that you can understand it very clearly. So, this is about the portion called getting started with machine learning models and applications. As you know, application becomes part of the modeling. At the end of this course, you are supposed to learn all these models and use it using Python, and because Python is the language which is used to make or prepare codes for different kinds of machine learning based models. So, it is desirable that you get some training on Python. We will be integrating it slowly, few of the aspects of Python in terms of science script or science sci script, but you have to make your efforts much clear so that you understand how to apply these models. So, as a part of these third aspects, getting started with machine learning models applications, we have discussing today decision tree, right, and I have already discussed about linear models. So, let us first do recap. We must be thinking what is the use of these decision tree models or different kinds of machine learning models. Are there enough problems from material science domains, or can you describe these things from physical aspects or physical description of the problem is possible or not. So, I gave you a few examples, and I am telling you again, one of the important aspects of data driven discovery of theories and model is Hume-Lethierry rules. It was discovered by William Hume-Lethierry when he was a professor at the Oxford University, London, and he has, this is a classical work on data driven formula about the substitutional solution. All of you know liquid solutions, right. You can add sugar into water, you can form a liquid solution very easily. You can stir it and make a liquid solution. Solid solution is exactly same, but in a solid state. So, you can add like zinc into copper to get brass. You can add aluminum, nickel into aluminum, get solid solution of nickel aluminum. And you can even add various kinds of substitutional elements to get solid solutions also. But there are certain rules which dictate when solid solutions will form. The first rule is that atomic size factor, because since you are replacing one atom with the other atom, the size factors become very important, and it has been said that the relative difference in the atomic diameter between the solute and the solvent must be less than 14%, then only substitution solutions are possible. Similarly, there will be electrochemical factors or valency factors. Electrochemical factors tells you probability of forming substitution solutions will be larger when the difference in electronegativity between the two elements is about 0.4, or it should be less than 0.4, not about 0.4. Okay, and valency should be not much lower, so that they can dissolve into each other. And last one is the crystal structure must be similar. So, we know these aspects which was described by Hume-Lethierry almost 100 years ago can be obtained by data driven discovery, because you have a lot of data from solid solution formations. You can easily analyze and make a model out of it and find out that these features, these aspects like atomic size differences, electronegativity, valency and crystal structure, there must be 4 factors that will dictate the solution formations. So, by feature we mean the variables, these are my variables and this is the range of values of my variables. When you select 2 elements, whether they will form solutions or not, the decisions can be made by this applying these rules. You can also use Paris law for fatigue crack growth. Basically, most of the you all should understand the failure of the various objects or various instruments happen by the fatigue. Fatigue is cyclic load driven failure, and this is very important to know what is the maximum number of cycles a material can withstand before it fails during fatigue loading. So, Paris gave a formula which is nothing but like this: the crack growth with respect to the number of cycles. A is your crack length and N is your number of cycles. So, I can take a derivative of A respect to N, and this must be equal to a constant C multiplied by delta K to the power m. Delta K is nothing but the difference of stress intensity factors when there is a crack with respect to when there is no crack, right. That is the difference of stress intensity factor in these 2 situations, right. So, that is what is delta K is. So, this equation can also be derived using data driven approach. Last example I gave is Hall-Page equation, the classic equation which correlates the grain size of a polycrystalline material with yield strength. Sigma y is the yield strength, sigma I is the frictional strength, and K is a constant, and D is your grain diameter. So, it is basically we can write it even much simple way. Sigma I is proportional to root over 1 by root over dt d. Okay. So, that is it. So, this d should be small d, right. Why shall I write capital D? Let us write small d in order to make it similar. Sorry. Okay. So, this is very important or extremely important equation in metal industry, because mechanical properties for yield strength can be controlled by simply controlling the grain diameter, grain size. So, these 3 fundamental aspects I discussed actually demonstrate data driven discovery of various models, correct. Obviously, Hall and Page use lot of experimental data to get this equation, but this equation can be derived fundamentally also. There is a physics behind this equation, you can go back and read books, understand that. So, the point I am trying to make here is that this set of equations or this set of problems which I am discussing today are actually can be treated as a physics based machine learning modeling, because there is a underlying physics for both Paris equation as well as Hall-Page equation and Hugo-Theory's rules. So, fundamentally they are related, but we can also use this data informatics or data driven approaches to discover these fundamental equations. Well, I do not want to go back to these slides. What I want to discuss is that scikit learning, and this is a open source Python library which you should install in your laptop or laptop whatever, and you can use various tools. There are various kinds of tools available like NumPy, Matplotlib and many others, okay, which we will slowly discuss one by one, and you can use these tools. This is basically open source library, so anybody can use it. There is nothing like a payment of money or whatever. It's free of cost, and you can download anywhere where you have internet connections and install these Python scikit things and model it. So, now the last part of my last part means the last lecture actually discussed about something about logistic regressions. As you know, classification is very important aspects in machine learning for material science, and in binary classification problems we simply predict probability of a binary outcome, whether it is a 0 or 1, yes or no, based on the input variables. In linear regression we predict continuous values of any variable, right, or any level. But here we predict discrete values, simply 0 or 1, yes or no. So, logistic regression is sometimes called a binary classification, where output can be either 1 or 0 or no or yes, that is what it is. And this is ideal for any classification task. And this is very important that we use sigmoid function to do that. It is a basic function to use. The fundamental equation is this 1 by 1 plus exponential minus z, and this is how it looks like. So, you can see there is a diffuse boundary between -5 to +5, and beyond which less than -5 it becomes 0 and more than -5 become 1. So, therefore, this is basically a logistic functions which you can use, and these lines which are shown magenta colors, they are unit step functions, and this can be used for converting even any linear regression data to logistic regression data. I showed you in the last lecture, and this kind of equations provides you a domain. Domain means range of values. It has asymptotic behavior, as you can see on the both sides of the equation, both sides of the curve there is asymptotic behavior. It is monotonous, very monotonically increases, and it is differentiable. That is what is, these 4 factors make sigmoid function very useful. We will come back to sigmoid function, we will again talk about it when we discuss neural network, artificial neural network aspects. So, classification is very important, as you understand. I talked about it. It is a process of classifying things into subcategories. It is a very supervised learning process, and it is very important in material science. Let me tell you, we will talk about it next 5-6 lectures, we will talk about a lot, and this is very important. And to remind you, supervised learning is something where you use both, we have the data of both input variable as well as output variable, like we have input and levels, both the data available, so that you can actually map y as a function of x or many such variables, and goal is to approximate the mapping function so that we can have predictions of y when you have a new value of x. That is what is the idea is. So, this is supervised learning. So, classifications, as I told you, can be binary classifications 0 or 1, okay. Like on the basis of health conditions, we can always differentiate between the person is having disease or not. Or classification can be also multi-level classifications. This is basically we try to predict 0 or more classes for each variable. That is what it is, what they call multiple classifications. There is no mutual exclusion, because input example can have more than one level, okay. So, this has been observed in different domains, like auto tagging in NLP or natural language processing, where a given text can contain multiple topics, okay. Do you know that a given text can contain multiple topics? You write one sentence where each of these words can have multiple topics. Similarly, in case of computer visions, image can contain multiple objects. So, these are the where we use this multi-level classification objects. There are multi-level decision trees are there also, multi-level gradient boosting. I already talked about gradient boostings, and we will talk about random forest. So, multi-level classification is a very common problem in material science which handle that. So, here you can see there are 4 images, one truck, one a plane, sheep and a dog, okay. And machine learning model must differentiate or must learn from these objects or shape of the objects or whatever features of the objects, and then predict if a given image is given later on what is the object is, okay. So, that is basically called multi-level classification. That means, here you have different objects have different kinds of features, okay, or one object can also have different kind of features, like in auto tagging in natural language processing. Okay, so, let us talk about the decision tree. What is the problem statement decision tree? Okay. Basically, there is a large variety of materials. So, before I come back, let me just discuss one more aspect, so that we can understand decision tree better. Let us talk about that on the board. Okay. So, as you know, let us say that we are predicting whether a customer will buy a product or not, whether a customer will buy product or not. How can we show it in terms of decision in terms of a tree like structures? Okay, let us do that. So, first let us say if have, this is what is my objective, if income of the customer is more than 50,000 rupees, correct. If this is the case, then answer is yes. Now, we can also have fact that age, if age is more than 30, like some of us, then you also have two different options. One is yes, third factor is whether the person has history of previous purchase, whether person has already gone to the same shop and had history of previous purchase, and I put a previous purchase more than 0. Let me write it much better way, so that you do not get confused. Okay. And then we say yes, purchase is made. Okay. So, if the income is more than 50,000 rupees, age is more than 40 and previously has made some purchase, likely that person will make the purchase, everything yes. Now, you can also situation no. So, income is 50,000, but age is also more than 30, but person does not make purchase. So, no purchase. Okay. See here also you can also have no. And obviously, with income is less than 50,000, there is no chance of purchase. So, if you look at carefully this is a tree like structure, right. So, you can clearly see the first root at the beginning we have something like a condition where income must be more than 50,000, then only things can happen. If it is not valid, if it is no, then there is no purchase done. So, first of all you have to look at customers whose income is more than 50,000 monthly, right, rupees. But that is not the only factor. Even if it can have, the person can have more than 50,000 rupees as income, monthly income, still he or she may not purchase. Only when age is more than 30 and the previous purchase histories are there, then only purchase will happen, otherwise it will not happen. So, this is a tree like structure which makes to understand how decision is made, correct. You can clearly see it is a tree like structure, and everywhere some subdivisions are made, and in every subdivision there are some decisions are made like yes and no, right. So, this is what is called a decision tree structure. Okay. That is what we call a decision tree. Okay. Decision tree is very important in our domain, I told you, because we make various decisions based on this tree like structure. This is what is called a decision tree like structure. Okay. So, if I have to put it all this no as a red color, then you can understand there is a branch like this, no, no, right, no, the 3 branches of no. So, now if I have to put this thing to perspectives, okay, let me put this thing into perspectives, let us hope this works. So, the first one, this one is called root, right. that is what is the root, that is what my basic feature from where everything started. This is what is called a root of the tree, right, from where everything started. Am I clear? And this is called internal, these are all branches obviously, internal node, correct. Each one is internal node, this one, this one, this one, all internal nodes. Why? Because at each internal node there is a one decision made, right. You see at this is a feature, age is a feature like an income, and here you are making a decision, right, yes or no. Similarly, this is a feature whether person has made a previous purchase or not, we are making a decision yes or no. So, these are all called internal nodes. So, remember this is called root node, this is called internal node, this is also internal node, please remember that. Now, obviously, the last thing where the tree ends is called a leaf node. Tree is ending here also and there also, many places actually, is called a leaf node. Okay. So, if I have to put in square brackets, this is called root, this is called internal node, this is called a leaf node. Remember these names, because at the leaf node the tree has stopped, there is no further progress of the tree, it is ended there, that is why I call it leaf nodes. Okay, remember this. So, root node is the questions was, first question was the person has income more than 50,000, right. If yes, you go to the next step, if no, you do not go. So, you stop here, that is also called a leaf node. So, this is also called a leaf node. It is just like a tree like structure, leaf I mean the leaf of a tree, okay, leaf node. And it can go on. So, internal node is age is internal node here, right. The person income is greater than 50,000 and age is more than 30, then something happens. Okay. And this is also internal node, right, this one is also internal node. Am I clear? So, that is it. Therefore, this is how we can make some kind of decisions, and decisions are basically based on the idea. So, now what do you think a decision tree is? It is basically a supervised learning. Obviously, you need all kinds of data x and y, supervised learning techniques, and used for both classification, mostly you are using for classification, classifying data, right, subcategorizing, that is called classification. Remember, classification means subcategorization, we are simply making different categories, right, that is what is called classification. And regression also, we have not discussed about it because I have not taught DT. Now, I can talk about how regression can be done using decision tree also. So, it is a hierarchical tree structure. Okay. Second aspect is it's a hierarchical tree structure. You can clearly see that it is a tree like structure, hierarchy from root to the leaf node, that is a hierarchy. So, that is why it is called hierarchical tree like structures, and it has a root node, it has branches. So, what are the hierarchical tree like tree structure has? This tree structure has roots, root actually, and it has branch, and it has leaf. What else it has? An internal node, right, internal node. These four important aspects: leaf node, internal node. So, on each internal node you are making a decision, right, at each internal node you are making a decision. On the leaf node your decision is frozen, you cannot further move, correct. That is the common structure of a decision tree. Okay. So, I just gave you one example, I will give you several examples now in the slides. Okay, please try to understand these ones. I will give you several examples. Okay. So, let us talk about this. I discussed it in the last lecture, I will talk about this more. So, as you understand, this is how you have to decide on material. So, a material can have cost, there are 5 features here, right, the 4 features: cost, strength, corrosion resistance and weight. So, cost can be low, medium, high, strength can be medium, high or low, obviously. These are all relativistic term. Okay. No specific values are given. Corrosion resistance can be either yes or no, weight can be lightweight, heavyweight or medium weight. Okay. And so, if you look at this, this is a chart. Low aluminum is a low cost, medium strength, high resistance, lightweight material. Steel is a heavy, low corrosion resistance, medium cost and high strength, right. That is how it is defined. Plastics is a lightweight, it has very high corrosion resistance, strength is low, cost is also low, right. So, if I have to put this information in a tree like structure like that, what we can do? So, you have to use some rules, right. Like here you have used rules. If the income is more than 50,000 and person has age more than 30 and also purchase history, previous purchase history, then only likely that person may do a purchase, right, otherwise it is not, right. So, this is the rule. Okay. We have to use certain rules. So, therefore, high cost is high or medium, you look at the materials actually, cost can be high or medium, strength obviously high for steel, corrosion resistance is not there, weight is heavy, that is called steel. Aluminum, cost is low or medium, strength is obviously higher medium, high corrosion resistance and weight is light, that is aluminum. Composites, high cost, high strength, corrosion resistance is high, lightweight. Plastics, I already talked about it. Titanium has a high cost, high strength, high corrosion resistance and very medium or lightweight. This is how each elements are differentiated. That is what is the rules. So, you can use these rules. I go back to this is upside down. So, you have a strength as the root, right, like here you have a root of income and you are dividing low, medium, high strength. So, plastic has a low strength, aluminum has a medium strength, steel has a high strength, right. And the high strength you can then from the next category is the weight, next feature. So, weight can be light, medium or heavy, you can see, and the third one is a cost. So, you can easily make a tree like structure like this. So, if you want a high strength material, low weight, lightweight and low cost, to go to aluminum, right, or medium cost. If you want a high strength material, high heavy weight, you go to steels. Okay. That is how you can make easy decisions. So, that is what is that, what does it mean? All this tabular data, whatever you have, based on certain rules, you can classify it in a very nice manner. This is what a decision tree does. We will discuss more about it in the next part of the lecture. Let us stop it here. We will come back in the next part of the lecture.